Okay, everyone. So this is the fourth chapter. It's kind of considered, I consider this your last chapter, even though we're going to delve into chapter 5 just a little bit. Chapter 4 is really the end of working the problems. Chapter 5, we're just going to introduce the second law of thermodynamics, and then it will be tested on just conceptually. But the fourth chapter, control volume analysis using energy, is really our last real chapter. So I'm just going to go over again a lot of the volumes. You'll see a separate video with a lot of the examples worked, but this is just going to be kind of conceptual information and information that you'll use on the quiz and on the upcoming exam. So you have your mass volume rate. Of course, that's denoted with M for mass, and then with the power above it, that denotes rate. And then that V is velocity times cross-sectional area times density. And then your volumetric flow rate is volume with the power equals cross-sectional area times velocity. And here's the units for those. And we haven't, just a note here, we haven't looked at the conservation of mass before because our mass has always been constant. Remember, we've always looked at closed systems before. Everything that we've done up until this point has been a closed system, and we know that from closed systems, mass is constant. So now that we're looking at open systems for the first law of thermodynamics, we have to take that into account. So here's the conservation of mass formula. It's also known as the continuity equation. And here it is. It's just summing in mass, rate, in and then out. And then you'll notice down here for the closed systems, the first law of thermodynamics equation that we've been using, and then that broken down into total energy. And then again, you'll see that first law of thermodynamics for open systems, the change in energy for the system over the change in time, and then that equals the total energy in less the total energy out. And so here is a little diagram on the side that just shows something similar to an open system, a very basic one, and then just the inlet in with the mass flow rate in, and then the outlet where the mass flow rate out is. And then again, you'll see heat transfer and work occurring at the boundary. So here's just a water heater example. At the inlet, the total energy in equals kinetic energy in, potential energy in, and U in. And again, you can divide this by M, or the mass, to get it into specific terms. And then again at the out, it's the same thing, just it going out. And then again, you can divide it by mass to get the specific version of this. And then the energy flow rate, which is denoted by a capital E with a power, is associated with the stream, is proportional to mass flow rate. So at the inlet, you've got the energy flow rate in equals mass flow rate in less energy flow rate in. And then again, we can always take out the mass to get it into specific terms. This is when you start using where you can use your tables to get your data and things like this. So that's why you would continue to want to use this in some instances. And then at the outlet, it's just the same thing, just everything is denoted by out. And then you see that the elevation change takes into account, so that's denoted by Z. So for heat transfer and work, you have the rates. And so when you have heat transfer rate entering the system, it goes from a positive to a negative. And then when you have a work rate entering the system, it goes from a positive to a negative as well. And then you have the equation here, which should look very familiar from the recent page. However, we do add it at the beginning of the equation because heat transfer will be happening right when it enters the system. So it's put at the beginning, and then the same for work. So this is taking our previous example and then including that method, whether it be heat transfer or work. And we add that at the beginning because when we're talking about an inlet or an outlet, these changes, this heat transfer and this work change is happening right as it enters the system or right as it's being pushed out of the system. So we include that at the beginning of our formula. Here's the power equation. Change in energy over change in time equals rate of energy in less the rate of energy out. And so because we have that power equation and you've seen it before, we can plug that in. And you see that here down below. And so that's just the change in energy over the change in time less that heat transfer rate and that work rate that we just spoke about up front at the beginning of the equation, added that with those other terms that we've been using, and you'll see that mass is pulled out and then less out, so in less out. And just a note here again, because it's an open system, we must account for shaft and electrical work in addition to boundary work, which makes this way more difficult. And the problem is that fluid is flowing into the system, does work in addition to the energy it is carrying. And this kind of work is called flow work, injection work, and boundary work. So what we've been working with thus far, because it's been a closed system, we haven't really been working with anything being added to it aside from heat working at the boundary, but not so much an entire different mass, right? An entire different system pretty much coming into it. And so we now have to account for that as well. So here's flow work. It's a force that is required to push a volume of fluid into the system. So pretty self-explanatory. And the surroundings are doing work on the system. Okay, so that makes sense. You've got what's inside of your boundary, and that's your system. And then when you have something flowing into it, then you've got the surroundings doing work on the system. A force is required to push a volume of fluid out of the system. And so then that is the system doing work on the surroundings. So that makes sense. That's just, at first you've got, because you're always referencing your system. That's what we've been doing in this class all semester long. We've been analyzing our system. That's what we look at. We are concerned about the system, but we have to account for everything else. So if we've got something coming in, then that is our surrounding, and that is affecting our system. But if we are pushing something out, then we are doing that work on the surroundings. So here's a formula for work. I kind of go through, this is really just extra information, just so that if you're interested in how we get some of these formulas, I don't break them all down just for time, but these are kind of the background steps in finding the formulas. But at the bottom, you can see that you have the flow work rate and then what that equals. And then you've got it at the inlet and at the outlet. And at the inlet, it's negative because the surroundings is doing the work. And then at the outlet, it's positive because the system is doing the work. And so recall, here's that formula that we just looked at a couple of slides ago. And this formula is very familiar to you guys now. And we can pull down work rate, and we can look at that from shaft work, electrical work, etc. And then we can pull it down again. And so now we're just, if you kind of look at each one of these, it's just simplifying, simplifying, and simplifying. And then when we get to the bottom, it's kind of like the last step. Can we simplify even more? Well, now we know that H equals U plus PV, and then we can sub that in for the first law of thermodynamics for open systems. So I boxed this in because it's really important, but if you're interested in looking about how we get from the first top equation all the way down, this is kind of a shortened path of how we get there, but basically the bottom equation is what you want to look for. Total enthalpy. So we talked a little bit about steady state process. So we learned in the first chapter that steady state is a state that is unchanging from one to the next. And we can model long-term steady state operations with these devices. It's turbines, compressors, nozzles, boilers, diffusers, etc. We are going to go through each one of these. Each one has a slide, and each one has different assumptions and things like that. Pay attention to these because they are, when you start modeling first law of thermodynamics for open systems, it's very much dependent on what you're using. So if we have not been looking at mass before because it's been a closed system, and now this change in mass and how this flow rate impacts our system is so important and it makes such a difference, well then how it impacts and how it leaves the system should be very important. Right? The shape of the device that we're using, or how many inlets we have, or what that device is used for, what can we determine from that? So all of that kind of makes its own little personalized formula. And so we're going to go through those. But we want to identify the assumptions for the steady state process. The first one is control volume is stationary relative to its coordinates frame, which, our system. No work done due to acceleration of the constant volume. State of the mass at each point in the constant volume does not change with time. And so if the mass at each point in the constant volume does not change with time, then this is 0, right? So change in mass, constant time over change in time. Change in mass, constant volume over change in time. Okay, so if we have these assumptions, then we know that we can go ahead and cross that out. And we did a little bit of that this past chapter where we were able to, well, hey, there was no mention of elevation change. So we were able to assume that potential energy was 0. So this is what we are also going to use to help tailor and simplify this huge formula that we just learned for the first law of thermodynamics for open systems. And therefore, this equals 0. And just to kind of put this in real world terms, basically means if 5 kilograms goes in, 5 kilograms comes out, no accumulation. So that's kind of what we're assuming, right? We're not getting in to the point of how efficient is this device, right? And so for something, I'm sure you guys remember me talking about this, but if something is 100% efficient, then this 5 kilograms coming in is going to also be coming out. Again, real world, we know that nothing is 100% efficient, but we have to start somewhere. And so this is kind of what we go on. This is our staple that we use, is that it's 100% efficient. And then we take the huge formula and equal it to 0. And then what this means as a formula is that it's a sum of all the inlet mass equals a sum of all the outlet mass, right? Because if you have 5 kilograms coming in and you have 5 kilograms coming out, so sum of all the inlet mass equals the sum of all the outlet mass. That means that we're at 100% efficiency here, okay? And this is our number 2 assumption. And then number 3 assumption is mass flux and state of mass crossing the control surface does not vary with respect to time. Steady state process, right? Mass flux and state of mass crossing the control surface does not vary with respect to time. Rates at which heat and work cross the control surface also does not vary with time. For steady state process with one flow entrance and exit, it's called single stream steady flow, SSSF. And again, mass rate in equals mass rate out equals our mass rate. And then we can pull that equation down. And then again, if we divide by rate of M, and here where Q equals heat transfer rate, constant volume over mass flow rate, and work equals work rate, constant volume, mass flow rate. And then I give you the units here. Okay, so now we're getting into those devices, and there's quite a few here. So what I kind of want you to do when you're looking through this is come back to these and think about what the device is doing and why we are Xing these out. Because if you look, we're using the same formula, the conservation of energy formula. You know that we always start out with that formula. If for no other reason, then you are in Thermo 1 and this is what we cover. But we always use this formula, and this is what we are going to be tailoring based on the device that we're using. So a heat exchanger is a device that is used to bring two fluids into contact without each other touching to exchange heat without mixing. Okay, so what you see down here in this little picture is a tube within a tube. And so the inner tube has the cold fluid and the outer tube has the hot fluid, and the cold fluid comes in once through the tube, and then the hot fluid comes in and circles around the cold fluid and then comes out, constantly flushing in hot fluid, keeping it hot to help heat up that cold fluid. And so again, it's to exchange heat without fluids touching. And what do we know about how heat transfers naturally? Heat goes from hot to cold. So examples are car radiators and air preheaters. Assumptions are steady state. All of these will be steady state processes. So all of these devices fall under the steady state process, but you'll see it on each slide. The work equals 0, and that's because there's no shaft work, electrical, etc. Heat transfer rate loss equals 0, and this is because heat transfer with the surroundings, not between the fluids. And then KE equals PE equals 0 because the flow rate is very slow and elevation change is minimal. So you also saw this in the last chapter that if something was just negligible or very, very, very small, we just assume it to be 0. We've got the conservation of mass and then the conservation of energy, that formula again. We can, that the steady state does the first, change in energy, constant volume over change in time. Work equals 0, so you see that as 0. Heat transfer, you see that as 0. And then again, we are Xing out velocity and any kind of change in elevation. So you saw that Z did that elevation in our air conditioner example from the ground to the outlet. So that's why that is X'd out as well. And then you can rewrite that, and we have broken that down into heat loss by hot fluid and heat gained by cold fluid, just depending on what you're looking at. And so you've got Q hot, out less in, and then Q cold, out less in, and all you're referencing is mass rate of hot or mass rate of cold. And then again, conservation, Q hot equals Q cold, 100%. Okay. A nozzle, what is the purpose of a nozzle? It's simply to convert energy in the form of flow work into kinetic energy, resulting in decrease of pressure and to generate a high velocity fluid stream. So that's the whole reason for a nozzle, is high velocity fluid stream. So here's just a little diagram of it. Vn is less than V out because we are increasing that velocity, and then pressure in is greater than pressure out. Examples, rockets and water jets. Assumptions, again, steady state. Work rate, 0. Heat transfer rate, 0. Potential energy, 0. And then the conservation of energy formula, again, you see all of that. but you see that our heat transfer is 0, our mass flow rate is 0, and then again we're making Z 0. And then therefore at the bottom, just the rewritten simplified version of the formula. You don't have to go through taking it, unless it's specifically noted, from the conservation of energy formula to the nozzle formula. These are given to you, but I would like you to really understand why we're taking this formula and are able to decrease some of these things through the semester. Like last semester, you had to know all of these assumptions, and then you were just given the conservation of energy, and you were responsible for taking it there. And again, not using notes or anything like that. So it would be very beneficial, especially because all of you are engineers, for you to understand and know these devices, because there's a high likelihood that you are going to use them if you're not already using them. Diffuser is just the opposite of a nozzle. It's the purpose to decelerate a high velocity fluid. So again, velocity in, velocity out, pressure in, pressure out is going to be flipped. Example is an aircraft exhaust. Assumptions: steady state, work rate is 0, heat transfer 0, and potential energy 0. I didn't break this one down because it's so similar to the nozzle, because it is in reverse, that it ends up being the same formula at the end. Okay, so our next one is a throttling device. Its purpose is to reduce pressure of a flowing fluid, and the example is a valve. The assumptions, again, steady state, work and heat transfer rate, both 0, potential energy, kinetic energy, both 0, conservation of energy formula. Here it is all mapped out. Again, with our X outs, velocity and elevation change both are omitted, and then here it is just deduced to the formulas. So we have next is a turbine. It converts flow work into shaft work, and it increases pressure. So this one is a little bit different. I didn't give a formula for it, but I did want to give some conceptual information for it. We've got a steam, where steam enters and exits through a condenser, a gas, which gas enters and exits through the atmosphere, water we don't consider here, and then there's 2 processes inside. 1, fluid expands to lower the pressure, and then 2, high velocity is reduced by rotating blades, and it transfers kinetic energy to shaft work. So that's how the work is converted into shaft work. We've got a compressor or a pump, and then of that, compressors are designed to handle gas. And so here's a little description of one here. And examples of that are rotary types, and they are opposite of a turbine. The assumptions are steady state, potential energy 0, heat transfer rate 0, and inlet kinetic energy is negligible, but again, we're just gonna assume that it's 0. And here's that first law formula. Again, really long, but we are able to X out some of these things with our known assumptions. And then here's the formula at the end. And then B is the piston tilt cylinder type, where the heat transfer rate is significant, and the fins and cooling jackets are to promote the heat transfer. Much less assumptions, steady state, and then just potential energy 0. So we're not able to X out a lot in here, so you see a lot of that left over in the final formula for the first law for piston cylinder types of compressor pumps. Mixing chamber, which I actually think a couple of the students in this class are using them, or at least work at places where they are being used. But this is when 2 fluids or more, this example is just for 2 fluids, are coming in to mix and then exit through a single outstream. So assumptions, steady state, Work and heat transfer rate are both 0, and then potential energy is 0. So you just have that formula down at the bottom. So boiler is to heat a fluid. Condenser is to change phase from vapor to liquid. And then evaporation is to change phase liquid to vapor. And the assumptions for all of these are the same. They are steady state, work rate is 0, potential energy, kinetic energy, still 0, and then pressure is constant in this. And then the first law, we're able to X out these, and then therefore you have this formula at the bottom. So now we'll get into transient process. Basically, what I want you to remember about transient process, or how I want you to remember it, is that it involves unsteady flows. So filling, discharging a closed tank or vessel, and then here are our model assumptions. Control volume remains constant relative to the coordinate frame, and then state of mass within the control volume can change with time. So that's the difference, right? Because we have been looking at everything else, but all of those steady state processes were not changing with time. So this is the difference. State of mass within control volume can change with time, but is uniform throughout the CV at a particular instance in time. Okay, so the mass flow rate may vary with time. The state of mass crossing the control surface is constant. So that's your difference. I'm sure that you got to that second bullet point and you were like, what? But the mass flow rate may vary with time. So the mass flow rate that we've been talking about throughout this PowerPoint. And the state of mass. So the state of mass crossing the control surface is constant. Here's the transient process, the conservation of mass formula, and then it is integrating over a period of initial state 1 to final state 2. In this situation, there are 2 states. So just 2 little schematics down here. Mass in, which is just everything filling the system. And so right now it's closed. And then state 2, we have kind of lifted that up and opened it. And it's everything leaving the system. So the state has stayed the same, right? The mass state has stayed the same, but the flow rate has changed. It's varied. Conservation of energy formula for transient process, and then again integrating over a period of time from initial state 1 to final state 2. Here's just the formula for that. And so then you can get energy, which is total energy equals kinetic energy plus potential energy plus U. And then we can pull that down and substitute those in for this really long, beautiful transient process formula. So that's the end of this PowerPoint for Chapter 4. Okay, thank you.